Hi everyone, first of all a very good morning to all of you. This is continued part of previous lesson where I am discussed about postulates of coordination chemistry. Today in this lesson, we are discussing about splitting of metal d orbitals, cluster field splitting in octahedral complexes. Okay, right. Octahedral complexes. First, we have to know the geometry of octahedron. If you see the geometry of octahedron, this is the geometry of octahedron. So here, yellow ball which is represented by center metal atom, and white balls are the ligands. Here we are having 6 ligands. Okay, so 1, 2, 3, 4, 5, 6. Okay, 6 ligands donating 6 lone pair of electrons to the center metal atom, forming coordinate bonding with this center metal atom. Right now, if you see the structure, if you consider this axis, x-axis, okay, along x-axis we are having 2 ligands. So along y-axis we are having 2 ligands. Along z-axis we are having 2 ligands. That means, so what you can understand from this structure, ligands donating electron density along x-axis, y-axis, z-axis. That means ligands approaching center metal atom with their electron density along x-axis, y-axis, and z-axis. In the previous class, I told you d orbitals can be split into 2 sets, that is T2G, EG. So dxy, dyz, dzx comes under T2G, triply degenerate Jared orbitals, and dx square y square dz square, the loops along the axis, dx square y square and dz square. So where electron density along the axis. So those 2 orbitals are called EG orbitals, doubly degenerate Jared orbitals. Right. Now before forming complex, all the 5 d metal atoms, 1, 2, 3, 4, 5. So dxy, dyz, dzx, dx square y square, dz square. So all the 5 d orbitals are in same energy. Okay, all the 5 d orbitals in degenerate state. Degenerate means same energy. Right. Now, and the next thing is here an hypothetical state. So that is when ligands are approaching symmetrically. From all the directions. There is electron-electron repulsions between the ligand orbitals and the metal d orbitals. So because of that electron-electron repulsions, the energy of 5 d orbitals rises somewhat. Okay, 5 d orbitals energy rises somewhat. Okay, increases. And next, the structure. In octahedral geometry, the ligands are approaching electron density along the axis. So here we are having two sets. One is dxy, dyz, dz, T2G set and EG sets. While ligands are approaching along the axis, in between along the axis, that means EG orbitals having higher energy, T2G orbitals having lower energy. Because EG orbitals, what are EG orbitals? Dx square y square, dz square. Okay, so EG orbitals having more energy and T2G orbitals having lower energy, because T2G orbitals are in between axis, dxy, dyz, dzx. EG orbitals are higher energy. Okay, right. So T2G, dxy, dyz, dzx and dx square y square, dz square. And this splitting is called cluster field splitting, and the difference is called delta cluster field splitting. And the cluster field splitting energy, and this is octahedral complex, the subscript O you can use, right? This difference is called cluster field splitting, and the energy gap between these two is called cluster field splitting energy or cluster field stabilization energy, CFSE. Okay, right. So this is the d orbital splitting in octahedral complexes, cluster field splitting in octahedral complexes. Right. Now this is the energy barriers, center, origin. So the energy difference, so lower energy, we take a negative charge, and you have 3 orbitals, right? So that means this is 0.4 delta O, and this is plus 0. Delta O. Okay, right. So 0.6 delta O and 0.4 delta O, or one more unit you are having, that is delta O is equal to 10 dq. So dq, differential quantity, that is also unit for energy, right? So 0.6 delta O or 6 dq or 4 dq, right? Now, if you want to find out the crystal stabilization in CF energy for a particular complex, you have to know the electronic configuration. For example, I am taking one complex here, TiH2O 6 times 3 plus. Here titanium 3 plus, oxidation state of titanium here 3 plus, and the electron configuration is 3d1. So actually 3d2 4s2. Now losing 3 electrons, after losing 3 electrons, the electron configuration becomes 3d1. Here having 1 electron. Now 1 electron which is occupies at lower energy. According to our principle, first we have to fill lower energy and then higher energy, right? So electron occupies the T2g orbital, right? So energy difference. Now CFSE of this particular complex is crystal stabilization energy CFSE is equal to 0. So the energy of the lower set T2g orbitals is 0.4. That means minus 0.4 into how many electrons here? Only 1 electron. 1 plus and higher energy, that's 0.6. 0.6. Here we don't have any electrons, so 0.6 into 0, so it comes out to be minus 0.4 delta O. In this way you can calculate crystal stabilization energy also. Okay, right. So this is crystal splitting in octahedral complexes. So simply in the metal in free state. So before forming complex in the metal in free state, in the free state all the 5d orbitals having same energy. Then after ligands are approaching symmetrically, then there is electron repulsions between the metal d electrons and the ligand electrons. In that case, because of that electron repulsion, the energy of 5d orbitals raises somewhat. Okay, and then based on approaching of ligands in octahedral complexes, ligands are approaching along the x-axis, y-axis, z-axis, along the axis. Now in that case, Eg orbitals having more energy, because Eg orbitals, what are Eg orbitals? Dx square, y square, dz square. They are having loops along the axis. Here also ligands approaching along the axis. So Eg orbitals and ligand orbitals having more repulsions. So in the, that's why Eg orbitals having higher energy, T2g orbitals having lower energy. T2g orbitals having lower energy, because in T2, what are T2g orbitals? Dxy, dyz, dzx. Okay, so these 3 orbitals having loops in between the axis. That's why they are lower energy, lower repulsions, hence lower energy, right? Right. Next, tetrahedral complexes, crystal field splitting, d orbitals splitting in tetrahedral complexes. Tetrahedral complexes, right? Tetrahedral complexes. First, we have to know the geometry of the tetrahedral complexes. So what is the geometry of tetrahedral complexes? So this is the geometry of the tetrahedral shape of the tetrahedral complexes. So black ball which represents center metal atom and the 4 ligands at the tetrahedral corners, right? 1, 2, 3, 4, and the bond angle is here 109 degrees 28 minutes, right? Now, so if you see that here ligands are approaching in between the axis. If you consider the axis, so this is x-axis, okay, right? So this is the tetrahedral geometry. Now this is x-axis, and this is y-axis, and this is z-axis. Okay, consider x-axis, y-axis. Okay, x, y, and z. So here ligands are approaching. This is x-axis, and this is y-axis. So ligands are approaching with their electron density with the metal atom in between the axis. In between the axis. So which set of d orbitals having more repulsions? Yes, T2g orbitals having more repulsion when compared to Eg orbitals. So this is exactly opposite of octahedral complex, right? If you see the splitting, right? Now 1, 2, 3, 4, 5. Okay, sorry. So 5 d orbitals. 1, 2, 3, 4, 5. So 5 d orbitals. So 5 d orbitals. It's a degenerate state. So degenerate before approaching ligands. Metal in free state, the 5d orbitals in metal are having same energy, degenerate state, right? Next, so because of electron repulsion, the 5d orbitals energy raises in the same manner. Here also the energy is same, degenerate orbitals, but the energy increases because of electron repulsion. This is the hypothetical condition, hypothetical state, right? In the next case, here based on approaching of ligands, which one having higher energy, which one having lower energy? In tetrahedral complexes, the ligands are approaching in between axis now, so Eg orbitals having higher energy, sorry, T2g T2G orbitals having higher energy, EG orbitals having lower energy, because T2G orbitals are in between axis, dxy, dyz, dzx. If you see the structures of dxy, dyz, dzx, loops are in between the axis. That means electron is in between the axis. Here in tetrahedral complex, ligands are approaching in between the axis. So T2G orbitals having more repulsions. So T2G orbitals having higher energy. T2. You don't write G here, just T2. Why? Because in the previous class I told you, so the suffix, the subscript G is used only when the orbital or the complex or the geometry having center of symmetry. So if you see the structure of tetrahedral complexes, is there having any center of symmetry? No, because so this is the center. Okay, if I am taking a point at this center, so at some point you are having one ligand in the opposite direction. If you are having same ligand at the equal distance, then that complex having center of inversion, right? But here you don't having in the opposite direction. Okay, so here one at some point here at some distance you are having one ligand in the same distance in the opposite direction. If you are having same ligand, then that complex having center of inversion. Before that, in the previous year, learning structure of octahedral complexes. In the structure of octahedral complexes, so is this having a center of inversion or not? Yes, it is having center of inversion, because so if you are taking the point at this center, if you are taking the point, so at some distance you are having one ligand in the opposite direction at the same distance you are also having same ligand. So this complex having center of inversion. Okay, I hope you understand. Right, okay, I will repeat it again. So center of symmetry. So octahedral complexes, if I am taking the point at the center, so at some distance you can find one ligand at this point in the opposite direction. If you find another ligand, the same ligand at the equal distance from this center point, then that complex having center of inversion. So this complex having center of inversion, that's why you are using T2G and EG. But in tetrahedral complexes, so here having center at the center, you are having center point. Now here one ligand, but in the opposite direction you don't having any ligand in the same with respect to this point. So this complex, this geometry of tetrahedral complex, okay, not having any center of symmetry or center of inversion, right? So you don't use G, just you write T2 and E. Okay. Now the difference is delta T. So because this is tetrahedral T, delta T, right? Now this energy, so this is the energy from the barrier center origin, right? Now this energy gap, so this energy gap is higher energy and this is lower energy. So this energy is 0.6 delta T and this is 0.4 delta T. Okay, so 0.3 into 0.4, that is 1.2, 2 into 0.6, that is also 1.2. So equal energy from the center. From the center you are having equal energy. You should have equal energy. So 0.4 into 3, 1.2, 0.6 into 2, 1.2, right? So this is geometry of tetrahedron. Splitting of tetrahedral complexes, right? Now if you calculate the crystal field stabilization energy, CFSE, crystal field stabilization energy, right? For example, taking complex any complex Ni or chromium Cr/Cl4 2 minus, okay, Cr/Cl4 2 minus, here chromium plus 2. So chromium plus 2, oxygen state is chromium plus 2. Actually this is dsp2 aberration, so this is square planar complex. So you take another example, tetrahedral complex NiCO4. This is sp3 aberration, NiCO nickel 2 D8. Okay, so 1 2 3 4 5 6 7 8. Okay, so D8. So you can fill 1 2 3 4 5 6 7 8. Okay, now 4 electrons in lower energy and 1 2 3 4 electrons in higher energy. Now these 4 electrons into 0.6 plus these 4 electrons into 0.4. Okay, 16 and this is 24. So crystal stabilization energy for this complex is 0.6 minus 0.6 into 4 plus 4 into plus 0.4 into 4. So which is equal to minus 22.4 plus 1.6. So minus 2.4 and 1.6. This comes out with 0.8. So delta T. So in this way you can calculate crystal stabilization energy also for different complexes. By knowing the electron configuration of the central metal atom and filling the electrons in these orbitals according to Hund's rule. Here one thing you have to keep in mind, strong ligands and weak ligands. With the strong ligands, electrons are paired up. This energy gap is more. In case of strong ligands, this energy gap is more. So for example, if you are having a D3 configuration, D3 strong field, 1, 2, actually third electron goes into the higher energy, but because of this energy gap, more energy gap, the electron paired up in the lower energy. In strong field complex, if it is weak field, D3 weak field complex. If you have weak ligand and the configuration is D3, in that case 1, 2, 3. Electron configuration is 1, 2, 3. E2, T2, 1. E2, T2, 1. If it is strong field, 1, 2, and 3. Okay. Instead of going to higher energy state, it is paired up in the lower energy state, ground state. Okay. Right. Next, third complex, square planar complex. Crystal is splitting in square planar complex. Square planar complex. So square planar complex. So what is if you see the shape of the square planar, just this is octahedron. It's just removing. For example, if you take this z axis, along z axis, x axis, y axis, z axis. If you remove two ligands from z axis, you can get square planar complex, right? So this is a square planar complex. Square planar complex ligands are along the axis or in between axes. Along the axis or in between axis. Here ligands are along the axis, along x axis, along y axis. Here no ligands present on z axis. That means repulsions along z axis are 0, right? No repulsions along z axis, right? So now here ligands are approaching along the axis. So which set of d orbitals having more energy? Which set of d orbitals experience more repulsions? Absolutely Eg orbitals. Okay. Why Eg orbitals? So Eg orbitals are dx square y square and dz square. So these two orbitals having loops along the axis. That means electron density in between along the axis. So this is center metal atom. In this center metal atom, you are having d orbitals dxy, dyz, dzx, and dx square y square, dz square. So dxy, dyz, dzx are loops are in between the axis. Dx square y square, dz square. So these two orbitals, Eg sets of orbitals are along the axis. So along the axis. So along the axis, and ligands also approaching along the axis. So d orbitals having along the axis, and ligands are also approaching along the axis. So these two orbitals having more repulsions. Because of more repulsion, they are having more energy. Right. Right. So first, the 5d orbitals having same energy. The 5d orbitals having same energy, degenerate state, the metal in free state. Next, in the hypothetical condition, because of electron repulsion, the 5d orbitals energy raises somewhat. And this is second situation, second case. And the next, here ligands are approaching along the axis. So Eg sets of orbitals having higher energy, T2 sets of orbitals are lower energy. Now G. So here, so this complex, square planar complex having center of inversion. If you see that, if you are taking the point at the center, if you take the at this point at the center, if you take the point at this point, here you can find one ligand here. In the same distance in the opposite direction, you can find another ligand. That means same ligand. Same ligands are equal distance with respect to this point. So this complex having a center of inversion. So you can use G. Okay, right. So which sets of orbitals having higher energy? Eg sets of orbitals having higher energy. T2G having lower energy. So this is Eg and T2G. So what are Eg orbitals? Dx square y square and dz square. And this is Eg and this is T2G, dxy, dyz, dxz. Okay. Now, here dx square y square dz. So, up to here the splitting of octahedron also same. But here, what is the difference between octahedron and square planar? Here in octahedron, we are having two ligands along z axis. That means repulsions along z axis. So that's why these two orbitals dx square y square and dz square having degenerate orbitals. These two orbitals are the same energy. These three orbitals having same energy. Okay. But here there is no ligands along z axis. There is no ligands along z axis. That means repulsions. There is no ligands along z axis. That means there is no repulsions along z axis. For that, so that's why. So these two orbitals again split into two energy states. So which one having higher energy? Dx square y square, because ligands are along x axis and y axis. So dx square y square having higher energy, and there is no ligands along z axis. So dz square having lower energy. Okay. Now coming to here also dxy, dyz, dxz. So here, so the ligands which are having z component are lower energy because no ligands are along z axis. So okay. So here dxy, so dxy and dyz and dzx both are having z components. So these two are degenerate orbitals, dyz, dxz. Okay. So this is the splitting in square planar complexes. Okay. I will repeat it again. Right. So in the first metal in free state, all the 5d orbitals having same energy. Next, after ligands approaching in symmetrical manner, we are getting a hypothetical condition, hypothetical state because of electron-electron repulsions. All 5d orbitals having same raises somewhat energy in equal manner, right? And the next, ligands are approaching along the axis, along the x and y axis. There is no ligands along z axis. So because of ligands are approaching along the axis, dx square y square dz square orbitals having higher energy. That means each sets of orbitals having higher energy, t sets of orbitals having lower. Up to here, the splitting of octahedral also same. But next here, what is the difference between octahedral and tetrahedral? So octahedral, square planar. In octahedral, the two ligands along z axis, but in square planar there is no ligands along z axis. So here further splitting takes place because these two orbitals are not same energy, because there is no ligands along z axis. So the dz square orbitals having lower energy. Okay, because no repulsions, because no ligands along z axis, right? So dx square y square higher energy, dz square having lower energy. Here also you are having z component, that is dyz and dxz. So these two orbitals having lower energy. So the orbitals those are having z component are occupies lower energy because no ligands along z axis. So this is all about Christoffel splitting in different geometries like octahedral, tetrahedral and square planar. Okay, let's move on to the next topic. So what are the factors affecting Christoffel's stabilization energy or splitting energy? So the energy gap. So the energy gap between T2G and EG, lower energy and energy. So this energy gap, what are the factors affecting this energy gap? So that is Christoffel's splitting energy. Now we are having 4 factors. Let's see one by one. The first factor is oxidation state of center metal atom. Oxidation state of central metal atom. Oxidation state of central metal atom. Right. So as the oxidation state of central metal atom increases, CFSE increases. As oxidation state of central metal atom increases, Christoffel stabilization energy increases. So because the ligands with their electron density, approach high charged metal atoms more strongly and more closely and forming strong field complexes. So for strong field complexes, the energy gap is more. Okay. I will repeat it again. Oxidation state of central metal atom. As oxidation state of central metal atom increases, Christoffel stabilization energy increases. That energy gap, that is Christoffel's splitting energy or stabilization energy. The Christoffel splitting energy increases because the ligands with their electron density approach high charged metal atom, higher oxidation state, high charged metal atoms more strongly and more closely, and interact most on forming strong field complexes. For strong field complex we are having a large energy gap, that means crystal splitting energy increases, right. For example, if you see FeCN6 3 minus, FeCN6 3 minus and FeCN6 4 minus. So, I am taking two examples here. So, FeCN6 3 minus, FeCN6 4 minus. So, which complex having higher CFSE? In which complex the crystal field stabilization energy increases, the crystal field splitting energy increases. For this in this complex iron, what is the oxidation state of iron here? Just calculate X plus 6 into minus, cyanide is minus 1 equal to minus 3. So, X comes out to be plus 3. So, iron here plus 3 oxidation state. So, Fe 3 positive, right. Now, here FeCN6 4 minus, here X plus 6 into minus 1 equal to minus 4, X comes out to be plus 2. Iron plus 2 oxidation state, right. Iron 3 plus, iron 2 plus. Now, which complex having a higher CFSE? According to first factor, oxidation state of center matter increases, crystal field stabilization energy increases. Here Fe 3 plus, the cyanide with their electron density approaching high charged metal atom more strongly and more closely. That means, so cyanide, so if you take these two metal atoms, so the cyanide approaching Fe 3 plus, cyanide donating its lone pair of electrons more preferably to Fe 3 plus and forming strong field complexes. So, Fe 3 plus means FeCN6 3 minus having more CFSE. Okay, let us take another example. CONH3 6 times 3 plus, CONH3 6 times 2 plus. Okay. Now, here cobalt, ammonia is neutral ligand, and here also ammonia is neutral ligand. Now, cobalt here plus 3 oxidation state, here plus 2 oxidation state. So, X plus 6 into 0 equal to overall charge, that is plus 3, X into 6 plus 6 into 0 equal to overall charge 2 plus. Because of ammonia is neutral ligand, the overall charge which belongs to central atom, that is cobalt 2 plus and cobalt 3 plus. Now, ammonia with their electron density, ammonia having one lone pair of electrons over the nitrogen. Now, this ammonia donating its lone pair of electrons to cobalt plus 3 metal atom, more preferably it donates lone pair of electrons to the cobalt plus 3 rather than plus 2. So, that means cobalt plus 3, that means ammonia ligand which forms strong field complex, which interact strongly, which forming strong coordinate covalent bond with the cobalt plus 3, okay, then cobalt plus 2. So, this complex having more CFSE when compared to this complex. Okay, understood? Right, that is the first point. And the second point, second factor was size of metal ion, or principal quantum number. So, principal quantum number, size of metal ion or principal quantum number. As size of metal ion increases, crystal field splitting increases, delta increases. Okay. So, why? Because, so if the size of metal ion increases, the area occupied by the d orbitals increases. Then the electrons present in those d orbitals will repel by the ligand orbitals more strongly. If more repulsions, the energy gap is more. Okay. So, size of metal ion, as size of metal ion increases, so our principal quantum number, for example, cobalt, rhodium and iridium. So, cobalt belongs to 3D, rhodium belongs to 4D, iridium belongs to 5D. Cobalt, rhodium is same group. Okay, cobalt, rhodium and iridium. Cobalt, rhodium, iridium. So, 3D, 4D, 5D. The principal quantum number. This is the principal quantum number. Shell number which represents shell number, that is 3D, third shell, fourth shell, fifth shell. 3D, 4D, 5D. So, as principal quantum number increases, crystal field stabilization energy increases. So, from groups top to bottom, the size increases. Cobalt and rhodium and iridium. As size increases, the area occupied by the d orbitals increases, so the electrons present in those d orbitals will strongly repel by the ligand orbitals, electrons present in ligand orbit, right? right. So that is second factor. For example, if we take the example, so I am taking this complex, cobalt complex, that is CO NH3 6 times 3 plus RH NH3 6 times 3 plus IR NH3 6 times 3 plus. I am taking 3 complex. So which complex having higher CFS? This is 3D, this is 4D, this is 5D. The size of central metal atom increases. Say same oxygen state plus 3 plus 3 plus 3. In all these metal atoms having plus 3 oxygen state and same ligands, same geometry, octahedral, because of coordination number 6, the geometry is same, octahedral, and the oxygen state also same. But the difference here, cobalt, rhodium and iridium. So cobalt, rhodium, iridium, the size increases. As size increases, the repulsion between metal d orbitals and the ligands increases. Okay, so energy gap increases. So one more thing you have to remember here, that is 4D, 5D metal atoms always form strong field complexes. They are always having higher CFSE. So whether it is a weak field ligand or strong field ligands. In 3D series, if the ligand is strong field ligand, the crystal stabilization energy increases. If the ligand is weak field ligand, the crystal stabilization energy decreases. Okay, so that is the third factor I will discuss there. But 4D, 5D metal atoms, even though it is weak field ligand, it forms strong field complexes. 3D, 4D, 5D metal atom always forms strong field complexes. They are always having higher CFS. They are having always a higher energy gap. Okay, right. So this is the second factor. And the third factor, nature of ligand. So nature of ligand. So the stabilization energy, crystal field stabilization energy increases with the increase in the strength of ligand. As strength of ligand increases, strength of ligand increases, delta increases. Strength of ligand increases, delta increases. That means, so those ligands which cause large splitting are called strong field ligands. What are strong field ligands? What are strong ligands? Those ligands which cause large splitting. Those ligands which cause large splitting are called strong ligands. Those ligands which cause small splitting are called weak ligands. Okay, so this can be understood with the help of spectrochemical series. So what is spectrochemical series? So this is very important. Spectrochemical series. Spectrochemical series. So spectrochemical series, arranging different types of ligands according to their strength. So that is the spectrochemical. So it is a series where you can arrange different ligands according to their strength. So that is spectrochemical series. So from this series, you can know which one having higher strength, which one having lower strength, which one is higher strong ligand, which one is weak ligand. Okay, so I will write it here. Right, CO greater than Cn minus, CO is strong ligand, then Cn minus orthophenanthrene, bipyridine, okay, NO2 minus ethylene diamine, NH3, which is equal to pyridine, also same strength. Okay, next NCS minus H2O, OH minus, at the end you are having halogens, F minus, Cl minus, Br minus, I minus. Okay, so this so cobalt, so in the this series is called spectrochemical series. In the front of the spectrochemical series, that is CO, Cn minus, orthophenanthrene, bipyridine, NO2 minus, all these are strong ligands. All these are strong ligands. Strong ligands are, another name is pi acceptors. So why these ligands are strong ligands? The energy gap between T2G and high. These ligands cause the gap between T2G and Eg, energy gap between T2G and Eg is more in the geometry, right? And next, the ligands which are at the end of the spectrochemical series, like H2O, OH minus, F minus, Cl minus, Br minus, or sigma donors. Sigma donors. So So they always donate their electrons to the center metal atom. But here they also donate lone pair of electrons to the center metal atom, and they are capable to accept the electron pairs from the center metal atom. That's why these ligands are strong ligand. Okay, not only they are donating electron pairs to the center metal atom, so they are having vacant anti-bonding orbitals. Vacant anti-bonding orbitals. Into that vacant orbitals, vacant anti-bonding orbitals, they are accepting electrons from the metal atom. If metal having more electron density, these ligands having vacant anti-bonding orbitals, so they are accepting electrons from the metal atom. They are accepting electrons into their anti-bonding orbitals from metal. Okay, so that's why these are called pi acceptors. So these are sigma donors. They are not able to accept electrons from the metal atom. So they are forming back bonding also. So what is back bonding? So this is called synergistic effect. Back bonding, they accept electrons from the metal atom. If metal having more electron density, so these ligands having vacant anti-bonding orbitals, so they accept electrons from the metal. Electrons from metal atom to into their anti-bonding orbitals, vacant anti-bonding orbitals. They forming back bond from metal to ligand. So first the bond is ligand to metal. They are donating lone pair of electrons to the center metal atom and forming ligand to metal bond. In the next, if metal having more electron density, these ligands are having a vacant anti-bonding orbitals. So these into this vacant anti-bonding orbitals, these ligands are capable to accept electrons from metal atom, right? So that's why these are called pi acceptors. In between these two, ammonia, NCS minus, all these are intermediate. They act as strong ligands and as well as weak ligands. Depends upon the oxidation state of center metal atom. If the center metal having higher oxidation state, ammonia acts as a strong ligand. If the center metal having weak, lower oxidation state, ammonia acts as a weak ligand, right? So this is spectrochemical series. So this is about nature of ligands. So the third factor is nature of ligand. As strength of ligands increases, delta O increases. That means CFSC increases. This is one series. This is called spectrochemical series, where you can arrange different types of ligands according to their order. Okay, right. This the first at the starting of the spectrochemical series, we are having strong field ligands. At the end of spectrochemical series, we are having weak ligands. Okay, right. So for example, let's understand with the help of example here. So I am giving you a few examples. Cr, Cn 6, 4 minus, Cr, NH3, 6, 3 plus, Cr, H2O, 6, 3 plus, Cr, Cl6, 3 minus. Okay, so here I am giving you 4 examples. So 1, 2, 3, 4. So which complex having higher CFSE? Which complex having higher CFSE? So if you see these examples, chromium, 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 chromium. In all these 4 complexes, we are having chromium center metal atom. And the oxidation state of center metal atom here, oxidation state is, so if you take 3 minus, so CnCN6 3 minus. Now chromium oxidation state is 6 minus, that is plus 3. Here the chromium oxidation state is plus 3. X plus 6 into minus 1 equal to minus 3. X comes out to be plus 3. Right here, Cr NH3 6. Because of NH3 is neutral ligand, the overall charge which belongs to central atom, that is chromium, that is Cr plus 3. Now here H2 was neutral ligand, so the overall charge which belongs to central atom, that is chromium plus 3. So Cr plus 3. And here Cl6 minus, Cl minus, X plus 6 into minus 1 which is equal to minus 3. X comes out to be plus 3. So that means all these 4 complexes which are having oxidation state plus 3. So same central metal atom, same oxidation state, but difference is here ligands. Here cyanide is acts as a ligand, here ammonia ligands, here water ligands, aqua, and here chloride ligands. Now which one having higher energy, higher CFS energy? So if you compare the strength of these ligands by using this spectrochemical series, so cyanide comes first, and then ammonia, and then water, and then Cl. Okay, right. So this complex, the first complex I am written. So this complex having higher CFSE, and then this complex. So 1 is greater than, 2 is greater than, 3 is greater than 4. This is the order of the CFSE. So when you compare the strength of ligands, right? This is third factor. Now coming to fourth factor. So geometry of the complex. So geometry of complex or number of ligands, right. So geometry of the complex. So if you are having tetrahedral, octahedral and square planar, so which one having more CFSE? So if you see the splitting, the last one, that is third one, square planar. So square planar having more splitting. There is a large difference between lower energy and higher energy. That means so square planar delta SQ, which having higher crystal stabilization energy. If you see the structure, if you see the splitting of d orbitals in square planar, the energy gap between lower energy and higher energy is more. So that's why in square planar complexes the crystal stabilization energy is more. After that, octahedral and tetrahedral. Octahedral, that is delta O and delta T and delta SQ. Crystal splitting in square planar, crystal splitting in octahedral, crystal splitting in tetrahedral. Right now, the square planar complex having more CFSE. There is a relation between square planar and tetrahedral is equal to 1 by 3 into delta O. Sorry, 1.3. So 1.3. So delta S equal to 1.3 delta O. So delta S is that means crystal splitting energy in square planar is more. Okay, in that way, delta O is equal to, so delta O is equal to 9 by 4 delta T, 9 by 4 delta T. So delta O is more when compared to delta T. So what is the conclusion here? Crystal splitting energy in square plane complex is more, then after delta O, then delta T. So this is an order. So that is the fourth factor. If you are having square plane complex and tetrahedral complex and octahedral complex. So which complex having higher CFSE? First square plane complex, and then after octahedral. There is a relation here. Square plane complex delta S is equal to 1.3 delta O and delta O is equal to 9 by 4 delta T. Okay, right. So these are the few factors which are affecting crystal field stabilization energy. Okay. So what are those factors? First factor is oxidation state of central matter atom. As oxidation state of central matter increases, crystal field stabilization energy increases. And the second factor is size of metal atom. As the size of central metal atom increases, stabilization energy increases. 3D, 4D, 5D. So 3D metal atoms and 4D metal atoms, 5D metal atoms. So which one are having higher CFSE? Absolutely 5D. So 4D, 5D having higher CFSE when compared to 3D. Right. And the third one, nature of ligands. Okay, the CFSE which is depends upon strength of ligand. The strength of ligands increases, CFSE increases. We are having spectrochemical series, so where you can find which one having higher CFSE, which one having strong field ligand, which one is weak ligand. So you can arrange different types of ligands according to their strength. The first at the end of the starting of spectrochemical series, we are having a strong field ligands. At the end of spectrochemical series, we are having weak field ligands. Okay, right. And then the fourth one is geometry of the complex. Square plane complex having higher CFSE, and then octahedral, and then tetrahedral. Right. So this is all about factors about affecting crystal stabilization energy. And the next, what are the merits? Merits of CFSE, crystal field stabilization energy. So merits of CFSE. The first merit is they successfully explaining the most favorable geometry of the complex. Most favorable geometry of the complex. So that is the first merit of this this theory. First theory, most favorable geometry of the complex. And the next, color, which was not explained by valency bond theory. Color of many complexes, many transition metal complexes. Okay, this second. And the spectra of many metal complexes, spectral properties also. So spectral properties, color, how the complex attain a particular color. So all these things I have explained in second unit, where I discussing about the unit spectrum, color and spectra of metal complexes. So color of transition metal complexes. So actually the color is which is explained by the difference, the energy, the electron transition between the lower energy to higher energy. When if you instead white light, so the lower energy electrons absorbing those energy white light and goes into the higher energy state. Again they are comes back into the ground state by emitting some wavelength light which is correspond to a particular color. So that complementary color which is actually shown by that complex. In that way here you can explain color and the spectral properties also. And next magnetic properties. Magnetic properties which is depends upon extent of d orbital splitting. If the d orbital splitting is more, that means in strong field complexes the pairing of electrons takes place. That means there are less number of unpaired up electrons. Instead of going into the higher energy state, the electrons are paired up if the energy gap is more. Hence the magnetic nature will decreases. Next in that way you can have next this theory is predicted out which one few complexes are forming outer orbital complexes and few complexes are forming inner orbital complexes. Few complexes are forming outer orbital complexes. Outer orbital complexes and few complexes are forming inner orbital complexes. This fact can be explained by this theory based upon strength of ligands. Okay, right. So these are the few merits of crystal field stabilization energy, and the first merit is more this theory explains most favorable geometry of the complex, and this explains color of transition metal complexes and the spectra of metal complexes and magnetic properties of different complexes, and this theory explains the fact that a few complexes are forming outer orbital complex and few more complexes are forming inner orbital complexes. So all these are merits of CFSE. Sorry, merits of CFT. Merits of CFT, just correct it, crystal field theory. Okay, right. So what are the demerits? So the demerits, so which are the facts which are not explained by this crystal field theory. The first demerit is this theory totally emphasis on metal d orbitals, totally concentrated on metal d orbitals, how the d orbital splitting and the influence of ligands. That means this theory mostly total emphasis total emphasis on metal d orbitals and completely ignores ligand orbitals. It doesn't give any information about ligand orbitals. Ligand orbitals. Okay, that is the first demerit. So this theory places total emphasis on metal d orbitals and completely ignores ligand orbitals. And the second thing is, so this theory doesn't explain charge transfer bands. Charge transfer bands. So charge transfer bands. And third one, charge transfer bands and spectra of many complexes. Charge transfer bands means charge transfer spectra, ligand to metal charge transfer spectra, metal to ligand charge transfer spectra. So because of that means if you see the example KMnO4, potassium permanganate, manganese having +7 action state. So in that there is no electrons in d orbitals, but it exhibits purple color, so violet color. Okay, so why? Because of charge transfer spectra. In the higher classes you can learn charge transfer bands and charge transfer spectra. Okay, next. It doesn't explain strength of ligands, not explaining strength of ligands satisfactorily. So strength of ligands. So why H2O? So why H2O appears at the starting of spectrochemical stage, then OH minus. If you see compare the strength of H2O and OH minus H2O. So OH minus at the end. Okay, that means OH minus. So why? For here considering ionic bond between metal and ligand, metal and ligand. So the bond between metal and ligand is ionic bond. So in that, if it is ionic bond, the bonds between ions is more strong. In that case, OH minus having more energy, more strong fields, more strength. But in the spectrochemical series, H2O occupies influence than OH minus. So the explanation about this fact not explained. This can be explained by ligand field theory, which is next theory. So that is not in your syllabus. So where you can explain why H2O is a strong ligand than OH minus. Okay. So these are the few demerits of crystal field theory. So first demerit is this theory places total emphasis on the metal d orbitals, completely ignores ligand orbitals. And the second thing is this theory cannot explain charge transfer bands of different complexes. And next, the strength of this theory does not explain satisfactorily strength of ligands. That means why H2O is neutral molecule. Actually, this is neutral and this is ion. So why H2O appears in the starting, then OH minus. Why is to be strong than OH minus? Okay, right. Thank you.